Okay, so we know what we're going to find already. Okay, we know the process. We know the not process. We know what we have to determine. We have to determine our stress A and B value, compare with our yield. Okay, and then we're going to select the diameter first. The purpose is to select diameter of the shaft. Okay, then after we select diameter of the shaft, then we're going to check is our stress above tau max or equal to tau max. Okay, so we're going to proceed. So as I said before the break, we are just going to put in numbers now. Okay, we're just going to put numbers now. Okay, so I'm going to still get that figure. So let's see what we have. Okay. So define our transformation, x, y, z. Okay. So we know that we have our px is equal to 2,500 pounds. Okay. And then we know that we have a torque in the x direction, which is 2300 pound-feet. And we have to change this to inches because our stresses are in inches. Okay. So 2300 multiplied by 12. So this is equal to 2,700 pound-inch. Okay. And then we have our moment in Z. So this will be equal to 1,500 pound-feet. So it's equal to 1,500 multiplied by 12. So this will be equal to 18,000 pound-inch. Okay, so let me do it again. 2300 times 12, 27600, 1500 times 12 is equal to 18,000. That's correct. Okay. So now, knowing all this value, we can immediately go and find our stresses. Yes or no? So the stresses that we're going to identify, right? So if we were to recap, where were we, right? So I'm going to draw this in. So we're going to find. Okay, I'm just going to draw 2D now. Okay, because we know that in plane will work. Okay, so we know. So if this is our transformation. Okay, so I'm viewing the element face on again. Okay, so this is our Z, right? Right. So we want to find what is our shear, right? And we know that we have forces coming in the x direction, or stresses, not forces, sorry. So we want to determine our stress x, our tau xz, which equal to tau zx. We don't know what they are. Okay. So let's find normal stress. Okay. So stress x due to axial load, right? So due to axial load, so stress x is equal to minus 2,500. Y minus is compression, and then pi c squared. Okay, I will define c, where c is the radius of the shaft. Okay, this is the radius of the shaft. So that's straightforward, isn't it? So now, due to bending moment, normal stress, due to bending moment, right? So you have stress x again. minus by the moment that we found due to the moment bending is 18,000. Right. 18,000 multiply by y, which is the radius, where you have the maximum showing stress, and then divide by I, which is pi over 4 for a shaft. Okay, c to the power 4. So this will be equal to minus 18,000 times 4, 72,000. Right, 72,000. I'm going to get rid of the c, pi c cube. Okay. So now we know due to the normal stresses, the x, this will be equal to minus 2,500, right, over pi c squared, right, and then minus 72,000 over pi c cube. Okay, so we know our stress x value now, right? So that is our stress x value. So minus, so we know that this is going to minus 2,500. No, let me simplify it further. Okay, so this will be equal to minus 2,500 c, big C, Eugene, minus by 72,000, and then this whole thing divided by pi c cube, right? So I just bring over c minus 72,000 divide by pi c cube. So objective is to find c, okay? Right. Then we also know that stress in the z direction is equal to 0, right? There's no stress z, right? If you look at the element over here, right? So this is our stress z. This is equal to 0. And then we have to find the torque, okay? The shear stress induced by the torque. So the shear stress is in the xz direction. This is equal to shear stress zx direction. So this is equal to TR over J. Okay. So torque, we found it out, is equal to 27,600. Am I right? Wait. The torque is 27,600. Multiply by C, the maximum radius, divide by pi over 2, the polar second moment of area. Okay, so this will be equal to 55,200 divided by pi c cube. Okay, so now we have everything already. Okay, now we have everything. Right, so now we have this is equal to 55,200 over pi c cube. I'm pretty sure when some of you are looking at all this now, you can say that I'm going to write a Excel spreadsheet for this, right? To calculate the loading shaft selection based on unique loading condition. Okay, that's how companies do it. Okay, right. Then from here, right. So let's recap what we have accomplished. Okay, so I'm going to copy this. Okay, and then I think I have enough space. Right. So now we have all the values now. Right. So now is basically solving Moe circle and incorporating Tresca's criteria to select the shaft the what I'm so tongue twist for the radius of the shaft, right? So we have to find stress A and stress B, and also we have to find tau max. Okay, we have to find the we are not necessarily find, but in order to find stress A and stress B, we have to identify the stress average. Okay, so find stress A and B. So we know that A and B is equal to stress average plus minus radius of the circle. Right? Okay, so like how I've drawn the 2D mole circle with you guys earlier. Okay, so if I'm going to draw 2D mole circle on what we are trying to do down here, so you are more clear, because there is a lot of layers in this problem. Okay, so it's sometimes good to refresh where we are. So this is our normal stress, right? This is our shearing stress, clockwise and anti-clockwise. And we want to, so we also know that this is the diameter of a circle, right? Right. So we have already acquired that the in plane has the largest what diameter, right, or largest radius, right, from here, from what we've done down here in our analysis, right? We from here we have identified, hey, that's the biggest diameter already. Do not worry about the mole circle on the other two planes. We already know that this is the biggest, so we're going to focus on that. Okay. So the next thing that we are going to do is we know that, or we have to find what is our stress average. Okay. And assuming that this is your point, what are the 2 points? Point X. Okay, let me draw a line across first. Okay, so this is our point X. This is our point Z. So we have to identify our stress average, right? So once we know this stress average, right, then we know we can we already know what is our tau xz. Then we can find the what radius. Okay, so after knowing the radius, then we can find our stress A and stress B, right? Okay, so that's what we are trying to achieve down here. Okay, so from here we're going to find the stress average, right? So we're going to find stress average, so we're going to determine the center of the circle. So this part is straightforward now. Okay, so this part, so center of circle, which is our stress average, is equal to stress X plus by stress Z divided by 2, right? So we know that stress Z for this case is equal to 0, as what you can see. So this is equal to minus 2500 C minus by 72,000. Okay, so I just need to put a 2 down here. All right, and we do a pi c cube. That's it. Okay, so that's the center of the circle. Then we need to find the radius of the circle. Okay, so the radius of the circle is your tau max, and we realize that tau max xz is equal to tau max zx. Okay, and this is also equal